just started recording. That's where we're going. So we'll be on track here with 12.3. I think. Come on. Okay. So we're going to talk about. Let's get it up and running. There's a lot of wordiness to this, and some of it I'm just going to sort of breeze over, but it's there if you want to kind of go back and read some of it. But a lot of it I'll just explain. So while we have some sort of open space here, so if I had a function that gave me the profit. All right, so that's telling me I put in X, and X might be the number of items we sell, right? Plug in a function, and somehow because of our data, we've got some function that would tell us what our profit will be. So the more we sell, the more profit we make, or something like that. So is that kind of clear? It's just a function. I plug it in, I get what our company's profit is, right? What we're trying to understand here in this class is what would it mean for the derivative of the profit function? What does that tell me? First function tells me how much profit I made. The derivative tells me marginal profit, a rate. So those two go together. We call it the marginal profit, but it's the rate. And that marginal profit specifically saying to the next item. I sell one more, that will be the profit of that next one, which is a rate. So it's a profit per item that we're getting at. Sometimes we use it to project out even further. We might use that tangent line to say, okay, if I sell 20, what more would I, because I could figure out how much more would my profit be. But that's what the derivative can answer, is how much more, but not, it really doesn't give me the answer to how much did I make, just how much more from a given point, right? So this is a rate, a marginal, so forth. So let's just kind of put it out there. What do you think this would be? What would it mean to have two little marks? The derivative of the derivative. So yeah, basically, you could put a parentheses, but they don't. So it's the derivative of the derivative. So what is the derivative? It's a rate. So if we take a derivative of a rate, what do we get? A rate of a rate. That blows me. I can't think of that very clearly, but it's how fast that rate is changing, or how slow, right? It's the rate of the change of the rate. So because that can happen too, right? So not only is our profit maybe increasing, so we'd have a positive slope, a positive rate, but it could be changing either quickly or it could be changing slowly. And that's what the second derivative is going to help us answer. So in and of itself, it isn't always an enlightening piece of information, but it does help us see how is the rate that we have going today, how is that going to change till tomorrow? Is it going to speed up, or is it going to slow down? So should we get in now? Is it real critical, or is the rate is it leveling off? Is it constant? Is it slowing down and we want to wait it out, or is it speeding up and we just better get in, or else we'll get priced out, right? People do this with home buying. When 6 months ago rates were going out and people were just crazy and offering all the money they could to buy a house because they thought they'd never get the chance. Interest rates went up, prices came down, and now people say, wait, maybe I'll wait it out. Prices will keep coming down. So it's all this stuff. And again, this is not about long-term stuff. 6 months ago, people were crazy to buy a house, who wanted a house, and now 6 months later, they're waiting it out for the most part. So that's what happens with these derivatives. Tell us sort of what's happening right now. Doesn't mean we should buy into it. I did that once, and it was a big mistake. So, because I bought at the top instead of buying at the bottom, so, and then the market crashed, and we do what we do. but this is a rate of a rate. So it's a little bit harder to, I mean, you can't really feel or taste or see it as much, but that's what we're dealing with. And what we're going to see is we're going to use it because it will help us determine what the graph looks like. Because we know what something that's increasing looks like, right? It's going up. But if the second derivative is also increasing, right? It's going up at a faster rate. So actually we get that that exponential curve, right? So it's going that way. If it's slowing down, which could be happening, at the top of a parabola, we're going to slowing down and then maybe going to go negative. That's a different shape. And that's what the second derivative will help us understand what those shapes of the graph look like. Again, some of the stuff we use it for, since we've got graphing tools and graphing calculators, it's not as valuable because we can graph it and we can see it. Okay. 30 years ago, when we didn't have the graphing tools, we had to use these tools to kind of figure out what was happening at the graph. Okay, because we just couldn't just plug it in and do it. Plug it in and maybe a week later. How many of you, I don't think any of you, have you ever done any programming on a computer where you had cards? Was your program, was each line in the program was a card? That's what I started off with at Portland State. And they fed it in the machine, had no monitors. You just type these things in and hopefully you didn't make a mistake and you get this printout and then next week maybe you got your answers. So that was 30 years ago, 40 years ago. I'm getting older than I thought. So one thing we can put our hands on though is this idea, this physical idea, which is not necessarily business, but we could make a business, it could be involved, is that there is a function that gives the position of a moving particle, maybe us in our car. If we're going from here to here, that's a position function. It tells us how long it, for every minute, where are we, how many distance have we covered. If we take that derivative, the position function, what do we get? We get the rate that we're changing distance, right? We call that speed, or velocity actually, because it has a direction whether we're going forward or backwards. So the first derivative becomes speed, and then how many of you guys have been in like a sports car that has a nice little kick to it? I remember when my dad's friend just bought a Pantera, which is an older sports car. Anyway, I got one, and when you hit the back, that's acceleration, right? So that's not just speed, but it's that the speed is getting quick, much faster. So if you've ever had that experience of your head going back, like that's acceleration. Of course, we also have it the other way. If we have to slam on the brakes, our speed is going down very quickly. We feel that same way with our bodies too. How many of you have gone on a roller coaster? How many of you love, the more wild the roller coaster, the more your derivatives are there. You're feeling those first and those second derivatives. That acceleration, it's not just the speed. Yeah, it's great to go 120 miles an hour, but I'll tell you what, it's more exciting to go from 60 to 120 real quickly. It's that acceleration. So if you're a speed junkie, you're really not a speed junkie, you're an acceleration junkie. So you're living on the second derivative. And that's the rate of the rate. So that's the one thing we can physically really understand. And actually, going on a roller coaster ride is probably the best calculus experiment you can do, because you can actually feel it each place. So again, this is where it gets a little wordy. I kind of just highlighted the second derivative, simply the derivative of the derivative. So it's the rate of the rate, how the rate is changing. So in this case, when we think of physical, how fast are we going, but how fast are we changing our speed? Are we hitting the gas to try to pass, or are we hitting that brake to maybe slow down real quick? So that's that acceleration, not just the speed itself. And so acceleration is the derivative of velocity. And velocity, which we could also refer to as speed. Velocity just has direction with it, but speed is just the number. So we could have a position function over time. If we took its derivative, then that's how we get velocity. So notice velocity is the derivative of position, acceleration is the derivative of the velocity. So I could just say, if I took the double derivative of the position function, I get directly to the acceleration function. Okay, so it's just kind of, that's how we do it. The thing is we never do the second derivative directly. We have to take that first derivative and then take the second derivative. There is, at least I've never seen any shortcuts. I guess maybe if someone's really into it, they might come up with certain specific shortcuts, but we don't use it. It's just it's 2 steps. If we were going to maybe go for the fifth derivative, which they do exist, so you could keep taking the derivative multiple times until you get to 0, right? And then you're always constant. But especially with trig functions, since they go back and forth, you could take, the 99th derivative, and then you want to find some patterns. Okay, so that's basically all this is saying. We can get to that, and I guess they use S for position. I like P for position, but we get our velocity is a derivative of the position function. Derivative of the velocity function is acceleration. And so we can list it all these different ways. And again, this is kind of the second derivative, so the derivative of the derivative, and they just go ahead and put the 2, list it like this. But again, you take the derivative of the first one, and then you take its second derivative. So that does give us acceleration. And again, if this was an engineering class or physics class, that's pretty much all we'd be considering with the second derivative. But since this is business, calculus, we'll move on to some other applications. But they give a quick example. So if the position function was x cubed minus x, then when we take its derivative, the 3 comes down, right? And you subtract 1, so you get 3x squared minus 1. So this would be the velocity here. This is position. So it would tell us how much distance has been covered. And then when we took the second derivative, this will give us acceleration. And notice they took the 2 times 3 gives us a 6. Subtract 1 from 2, you get 1. Take the derivative of negative 1, you get 0. So this is the second derivative function. And again, it's acceleration. And if we want to find out what's this acceleration at negative 2, you plug it in and you get it. You can find the position, you can find the speed, you can find the acceleration. But see, now we've got 3 different functions, right? One gives us the value, how much distance in this case. The second one gives us the rate, how fast is it changing. And then the last one, the second derivative, gives us the rate of the rate. How fast is the rate changing? And which direction is it changing? Okay. Okay, and they give another example. And again, whatever the position function is, take its derivative, and you have a velocity function, which is its speed. Take that derivative, and that's a second derivative, and you're down to the acceleration function. Okay, and for most of these, we're not going to get too funky on the derivatives. Okay, any questions so far? Okay. Some of the notation we can use, and this one, I like this one with just the 2 primes because that tells us the second derivative. But another way, if they go to that other, the German method of instead of, dx, dy, or actually would it be dy, dx, usually we put it this way, they'll put a 2 on the d to say it's basically the second derivative. So if we've got dy, dx, then it would be d2y dx2. So that's just another way you see it. That's the second derivative. If there was a 3 there, it would be a third derivative, but we're not getting into third derivatives, but you could. And actually, I deleted that part of the PowerPoint. They talk about higher orders, but we're not going to have you do anything more than the second derivative. So just know that this is kind of funky notation for the second derivative. Okay, I kind of like this one. To me, it makes more sense. It's just a second prime, so just get used to. But I looked in the homework. Occasionally, they'll ask for it this way. So when you see it, just say, "Oh, I got to take the derivative first, and then I got to take the derivative a second time." That's what they're looking for. Okay. And again, some examples. And notice you can't really just jump to the second derivative. I mean, if you do it mentally and you can hold it in your head, you could, but that you're really taking a derivative, getting an answer, and then you're taking a derivative again. You might not be writing it down, but I would, because I'll mess up. So, y prime is 3x squared, and now when I take the derivative of this one, y double prime, 2 times 3 is 6, subtract the 1. Now I feel comfortable. But if you skip that middle step, I'm lost, right? It's harder to see. You might be able to say, okay, yeah, that looks right. Okay, but again, one application is distance, velocity, acceleration. Okay, so let's give an example. There is from experiments that have been done, they can measure the effect of gravity. So they take an initial speed, initial distance of something falling to Earth, and they find that this function will give the height of the item if it's falling towards Earth. Okay, so you throw a ball up and it comes back down something. To find its speed or its velocity, we take its derivative, so the derivative of this, again, s naught is the initial speed, which is a number. When you take, it's a constant. You take its derivative, it's always 0, so that goes away. Derivative of negative 16t squared, 2 times 16 is 32, or actually negative 32, t to the first power. So that's our velocity function. What would be our acceleration function? It would be the derivative of the velocity function, which would also be the second derivative of the position function, and the derivative of negative 32t is going to be negative 32. Okay, t to the 0 if you want, right? So just taking that derivative, which means that gravity has, the acceleration at least, is a constant. You don't get it, you get so fast, you don't get any faster. They actually call that terminal velocity. You might speed up a bit, if you jump off of a ledge or something, you'll speed up, but you won't get any faster than 32 feet per second. That's still pretty fast. It's faster than I might want to be going, especially if you're falling and you see the ground coming. But you won't get any faster. Okay, your speed will not be able to pick up unless you have at least not because of gravity. And that's what the next page shows us. So again, we've got the negative showing us that it's going downward, right? And downward force of 32 feet per second. All right. And so that's the second derivative. Now, we're going to kind of expand this and not just talk about velocity and acceleration, because it's a business class, so we want to be able to apply it to profit, revenue, supply and demand type problems. And what this is going to do is it will help us in interpreting a graph. And we'll get into the details, but basically, what the second derivative will help us find out. Remember, last time what were we talking about? This is Tuesday, right? Last Thursday, what was our discussion about? Anyone remember? Did it, done it, forgot it, right? Maximum and minimums, makes sense? So, but notice when you have a maximum or a minimum, you get a certain shape, right? this is called, how many of you wear or have worn a contact lens? Okay, you got glasses and you look at them like this, you'll see our glasses are concave. They have a concavity. Contact lenses have a concavity, and that's how you can tell if it's inside out or not sometimes, because it's there, but you get the right. So this is what we call concave. This particular one will, and again, the writing will do it, but we're going to call this concave up because it can hold water, so it's like a goblet or something, so it's up. So if that's concave up, what do you think we should call this one? Concave down. Perfect. So those are the two types of things. So it's kind of like an umbrella. But that's what the second derivative will help us determine without actually having to look at it. Basically, if the second derivative of the function, so here's our second derivative of this function, if it is if it's positive, if it has a positive value at this particular x value, so we plug in any of these x values here, if it's positive, it'll be concave up. And the only way I remember this is positive things make you smile, right? Positive things happen to you, you're going to smile, hopefully. If you can't smile when positive things happen to you, then, so I just remember this gives a smile, so that's concave up. Concave down kind of looks like a frown, right? So maybe some negative things are happening. So that is when the second derivative is negative, we're going to have a concave down. And that's how I kind of just visually remembering it. If it's negative, if the second derivative is negative, I've got some kind of concave down. And then to highlight, notice this graph, if we follow along this graph, we're going, this is all concave down, even though we're going across it, right? And I guess if we came back this way, this is all concave up. What happens, so the second derivative is positive here, it's negative here. What happens when the second derivative that's negative comes in contact with the second derivative that's positive? How can we change from being negative to positive? It's a philosophical question too, but mathematically, what happens when we go from negative to positive? You have to pass through zero. No other way to do it, unless there's some loophole. So there's some place in the middle where we're going to find a second derivative equal to zero. And we're going to see that's an important part. It's called an inflection point. It's actually where the rate of the rate, right, the second derivative, is kind of the fastest changing. So it's an important part to be. But when we find where that second derivative is zero, that's how we find that inflection point. But I just want you to see is that graphically, it has to happen. If you're going to go from a second derivative being negative and then all of a sudden it's positive, it has to pass through zero, right? So it becomes less negative, closer to zero. It becomes zero. That's our inflection point. And then it's got to change over. And I say it has to, but sometimes there's some funky things that can happen. Some of our graphs might be undefined and stuff. But that's basically today's lesson. Okay, if you can understand that picture, that's everything you need to understand. Now we're going to look at some functions, and it might seem not quite as clear. Yes?
Is the inflection point where x is 0 and y is like a number? Like, are inflection points always going to be...
X may not be 0. It's at some x value.
Oh, okay.
The y value may be something else because it would be on the function would give us that. But the second derivative at that point would be 0. And that'll become clear as we look at an example. So we'll get to that second derivative, and again, the second derivative could be a function that has some sort of x in there. We set it equal to 0. When we find that is that is potentially a point of inflection. It isn't always, but it's a lot of times it is. And then we could also plug in these x values over here. If I plugged in this x value, again, I would find if I plugged it into the second derivative, I would get a negative result. Some value that would be negative all along here. And then if I do it over here in this part, if I plug this x value into the second derivative, I would be guaranteed to get a positive. And here's the thing though, is I'm just interested of the sign, so I'm not so worried about the value itself. Doesn't matter if it's positive 32 or positive 16, it's just that it's positive, I know it's concave up. So we're also going to use this to help us, if we don't see the graph, we could determine whether something was a maximum, right? Because this is a max, or a minimum. Over here we get a minimum. So we could find that when the first derivative is 0, right? And again, we've got other pictures that'll tell us, but the first derivative is going to be 0 at both these points. But if we looked at the second derivative and figured out whether it was positive or negative, we could tell whether we had a max or a min without ever looking at the graph. Because if we know it's concave down, that's going to be like a mountaintop, that's got to be a max, or at least a relative max, right? A local max. If it's concave up, I got to have a low part, so I've got a relative minimum there. So these are types of things I can do just by getting those derivatives, plugging in particular x values without ever looking at the graph. And that's how we used to have to do it. So I take you back about 40 years when I was an undergrad, and I was learning from Dr. Crittenton, who was actually a mathematician who served in the Korean War, and his job was literally to do math in a tent to tell them how, because then back in the 60s, when they were sending missiles off, they didn't have computer-guided systems and stuff. So he was having to actually do parabolas and figuring out where would it land, and so that was his job. And they didn't have the tools, computers and stuff to do it. He had to do it all by hand. So let's get into this. So we look at this, and what do you think? So both of these are increasing, right? They're going up. If I come from left to right, this goes up. If I come to left to right, this goes up. But they're going up in different ones. Which one's going up quicker? Yes, look here, I get my left and right. So this is quicker. Right? This one's actually doing what? It's slowing down, isn't it? It's getting kind of to a peak. This is going slower. And when we're talking faster and slower, or quicker and slower, we're talking about the second derivative. First derivative is going to be positive for both of these. And if we were to lay out some tangent lines, right, we'd see tangent lines are all going up, right? Tangent lines all have positive slope. And those aren't great tangent lines, but you get the idea. Tangent lines are all going to have positive slope. But you see this one over here, the slopes are getting faster. That's a second derivative. They're accelerating. The one on the right, g of x, it's slowing down. It's decelerating. So its second derivative is going to be getting smaller. So what we know here, and what kind of a shape do you call this for g of x? If we talk about concavity, is it concave up or concave down? Concave down, you got it. So it kind of spills water. So if you couldn't hold water, good. So this, what we would know is that the second derivative is the value would be negative, concave down. Not quite a frown, but getting there. This concave up, right, sort of like a smile, or at least has this concavity where it would kind of hold it this. So since it is concave up, we would also, if we plug in the x values to the second derivative over here, we would get positive values. Okay. Again, that's basically the teaching on these. And again, this gives us the words, the first derivative tells us it's increasing, but since it's getting steeper, that's telling us that the second derivative of f of x was positive, okay, concave up. So that's the one that went like that. For the g of x, we know that g of x, that the function's increasing, but the slopes are getting smaller. They're not negative, they're still positive, but they're getting smaller, and so that's telling us that the second derivative would be negative, and that's a kind of a concave down situation. So both are increasing, but the rate of that increase is different, and that's what the second derivative gives us. So here it spells it out, what we've already been talking about. Concave up means that we are increasing, right? The slope is increasing, in which case the second derivative is positive. So the second derivative is positive. Curve that is concave down, and again this would look, concave up would be like that. If its slope is decreasing, in which case the second derivative is negative. So concave down, like a frown. And then we talked about this point of inflection. That's going to be where the concavity changes. So if a concavity is changing, either concave down to concave up, or concave up to concave down, there's got to be some place, and it typically, as you can eyeball it, it's about sort of what you would maybe see about a middle place where concavity will change from concave up to concave down. That's where we're going to see the second derivative. The second derivative equals 0. And again, it would make sense, because if it's going from negative to positive or positive to negative, it has to pass through 0. Okay. And again, you have access to these, and they won't be all marked up, but some of the wording I don't like a lot of words, but sometimes they're helpful. Okay, so how do we locate inflection points? Take the second derivative, set it equal to 0. Again, sometimes you can see it, you can see whether that's going to be the case, but basically take the second derivative, set it equal to 0. There is possibilities where you could, the second derivative is not defined, you could get an inflection point, but that's such a special case deal. I'm not ever sure I've ever seen one, but I know that most of the stuff we're going to deal with are smooth curves, so it's where the second derivative equals 0. So let's take a look, something like this, and we can see a curve that's concave down going to concave up. There's got to be some place, if it's a smooth curve, where the concavity is going to change, and what we find is at that place where it changes, the second derivative is going to be 0. And then on the other side, again, we go from concave up to concave down. It's there. And again, sometimes you can kind of eyeball it on a graph. It's about where you would think it'd be. It's where you kind of can see that what that concavity is doing. But if we have the function itself, we'll actually also be able to verify it with the second derivative. So if we had this function, and if what they're telling us, if we had the function, so we were able to take its second derivative, and we plugged 1 into that second derivative, we should get 0, because that's what it's looking like. That's where where the inflection point is. If we plug in a 3, right, we should have the same thing. If we plug the 3 into the second derivative, we should also get 0 if it's an inflection point, which that's what they're saying to us. Everywhere else, notice concave up, we're going to get the second derivative. Whatever x value we plug in between 1 and 3, we're going to get a positive second derivative. Anything bigger than 3 or less than 1, if we plug it into the second derivative, we get negative values. And again, you can actually figure them out, but the important part is the values are going to be negative. And remember, what are those values? Those are rates of the rate. So it tells us the rates are decreasing. Now, the function itself still may be increasing. This is the hard part, is the rates are decreasing, but notice the function itself in some of these is still increasing. Sometimes it is decreasing on the backside, but that's still concave down. Okay? So a lot of things going on, and to me, you got to use a graphing tool. Look at the graphs. Look at the graph. Because it makes it come home. So this I'm going to go over a little bit lightly because they get really involved into what the consumer price index does, and there aren't any problems in the homework on consumer price index, but I left it, maybe some of you, that's a field that you're working in, so this might be of personal interest, but right now we don't have a lot of we don't have problems on it. So what they've done is they've plotted the value of the U.S. Consumer Price Index, which is basically, at one point it started out the cost of $100 worth of commodities that people would buy at the grocery store. And tracking that price, how it would change. I don't remember when it was $100, but that same bag of groceries now costs, in this case, $234 or maybe $233. So the price of that bag of goods is how they check how things are going. So what we're seeing here is overall over this time period, and these are months from September 2013 to August 2014, that bag of groceries was going up in price. It sort of leveled off here, but they fit a curve to it so that we can kind of talk about it. We've got concave up here, so what does that mean?
Positive.
What's that?
Positive.
The second derivative would be positive. Exactly. So that when the second derivative is positive, that means the rate is increasing, right? So it's increasing here. Somewhere along the line here, because we can kind of see a concave down up here, so somewhere in here there should be an inflection point, and that's sort of the place where the second derivative will be 0, but it's also a place where we get the most rapid change. So, but that's where a lot of times economists are looking for is, if I can predict where that inflection point is, and it might still get worse for a little bit, but it means that things are going to come back down. So the inflation, the cost of things could be coming back down. So if we can predict where that inflation, that we're at an inflection point, the problem is to know we have an inflection point. What do we need? We need to know that it's going to go down, right? So inflection points are one of those things that it's great if we know it, but we generally aren't going to be able to know it until we're past it. Because this could have just kept going up like that, right? For all they know. There is no inflection point, it keeps going. But whatever they did brought the inflation back down, and hopefully, we got one of these. That's what economists are always trying to do. But that's where they can, if you can kind of get a little bit ahead of the curve with the mathematics, maybe you could find a way to predict, is this an inflection point? And but it would be based on sort of presumptions about the future. Okay, and this is where, again, they fit a curve to it. They came up with a cubic function. So part of what we do is you take the data and if you get a curve that fits it, now we can use our derivatives, right? We could take the derivative of this function, and that would give us the rate of change. This one doesn't get too much into the second derivative, so I'm not quite sure why they had it, but they do use the first derivative, which in this case is always increasing. It's going up. And what economists do is they don't report the CPI necessarily by itself, but they want to report the change. So they use a relative, when they do the inflation rate, they do the rate of change of the CPI divided by the CPI itself. So it's kind of a hybrid. It's a relative rate of change of the CPI. Okay, and so I kind of want to get through this, but you could take the first derivative, we get that. You can see a given month, so 4 months, which was January 2014. We plug that in, and then we do the math on it. So here's the derivative at 4, here's the original function at 4, and if you do all the math, it ends up being a 0.36% per month increase. So slow increase, I mean, at less than 1%, but what we're facing right now at about 6 or 7%, I think they're saying our monthly inflation rate is. So this is not so bad, but it is an increase. Okay, and that's how they, the relative, the monthly change is what they're looking at. Okay, and again, I'll leave most of this for you to take a look at. They do get into what the second derivative is going to tell us. So the second derivative at 4 ends up being positive, which tells us we're concave up. And so all it tells us, okay, well, it's going to concave up means it's going to keep going up pretty fast, right? Because that means it's going to go like this. And if we're on this side of the curve, we're going up. And we're hoping for an inflection point, because that inflection point means that it will slow back down. But we won't know we're at an inflection point until we've passed it, really. Until on the other side. You got to get to that other side. But this is, this is what our economists use. They use derivatives and second derivatives and say, that's why when everyone else says, oh, the rate is going down, but is it going down fast enough? What about that second derivative? And that's why a lot of these economists are still, we still got a positive second derivative. They say that we know it's not over yet. We want to wait till it's actually coming down. So they can use that. And again, if we could find a good way to predict and know for sure that we are at an inflection point, that would be awesome. But we got to know what the future holds. And so far, people have tried to use math. There's a book, actually I read it, the Foundation series. Anyone read that one? They turned it into a mini series on Apple Plus, but it's about a mathematician who can kind of predict the future with math. Of course, it only works for large numbers of people and stuff, but it's science fiction still. Okay, so I think we'll go, most of what we need to do for homework, that's not part, but there's an application. So here's just a quick test that we can do. We know we can use the first derivative. When the first derivative is 0, that'll give us either a maximum or a minimum. Again, if we don't see the graph, we don't know whether it's a maximum or minimum. If we can take a look at the graph, we can pretty much tell. But if we can't see the graph, then what we're going to want to do is take a second derivative and see whether we're concave down or concave up. Okay, so second derivative here is negative. We're concave down. We know we're going like this. We know we've got to be at the top of the mountain, so we've got a max, right? If we take the second derivative here, again, we don't have the function. We'll look at an example. The second derivative, we plug in a value, because we found that b is a place where there's a critical value. We plug that into the second derivative to see whether it's positive or negative. This one, it would tell us it was positive, and so we would know we have a minimum. Okay, and you have to, for me, I always have to think backwards, because I would think a positive second derivative sounds like I'm at a maximum, but it's actually a minimum because gives you the smile, and a smile has a minimum. Negative gives you a frown, which gives you a maximum. Okay, so you can use that second derivative. You can also use a graphing tool to look at the graph. Okay. And again, you just kind of keep going with this. So what they do is, as they analyze it, this they call it the second derivative test for relative extrema, is you first find your critical values, which are what are the critical values? It's where the first derivative equals 0. Okay, so you've got a maximum or a minimum there, critical values. Critical So we find those, and then what we want to find out is what's the second derivative. Is it negative or is it positive? So that's what the second derivative test can do. If the second derivative at that particular point is greater than 0, which means positive, then we would have a relative minimum because it's concave up. If the second derivative is negative, that's what this part here is saying, then we'd have a relative maximum because it is concave down. Okay, so this is just another test that can be used. You don't have to. You could do it with the graph. Okay, but just think they may use a second derivative test. What is that? It's to figure out whether we have a maximum or minimum, but we could also do it with graph. There's multiple ways. We'd also look at the signs of the derivative itself, the first derivative, because at a max or min, we get 0, so on either side it's going to be positive. So if it goes from positive to negative, we've got a max. If it goes from negative to positive, we have a min. So what always got me off is there's multiple ways to do it. I could use a first derivative test of looking at how the signs change around that critical point, or I could just look at the second derivative, whether it's positive or negative. Okay, so they both give us the same information. My favorite, I'd like to just look at the graph because for most things I can tell by the graph. So they're going to use the same or similar type functions. So if f of x is x squared minus 2x, we take its first derivative, so the 2 comes down in front, right? Here's our first derivative. And so what we do is we want to find any place that first derivative, 2x minus 2, where does that equal 0? So we add 2 to both sides. 2x equals 2. Divide both sides by 2. So when x equals 1, we know that the first derivative is 0. So what does that tell us? We have either a maximum or a minimum. That's all it tells us. We don't know yet, unless we were to graph it. What would we need to find out to tell whether we have a maximum or a minimum? Well, let's take the second derivative. So if this is the first derivative, what is the second derivative? 2x, its derivative is 2. Derivative of negative 2 is 0, so that's it. So then, since this is where I have a critical point, I plug in 1 to the second derivative, and what do I get? 2. It's a constant. Is 2 positive? Yes, it is. So positive means it is concave up. And notice it's an x squared. It's got a positive on the front. So that's another way we could have told us. So it's concave up. We know that at x equals 1, it has to be a minimum. Relative minimum. And we could do that without actually even seeing the graph. Of course, seeing the graph would be helpful, but that's how we can use that second derivative test. That makes sense? Okay. Now, it could have been that sometimes the second derivative does have an x value, so you plug it in and you calculate. But again, the thing we're interested on the second derivative test is only the value, whether it's positive or whether it's negative. The sign, let me put it that way. We're not interested in the value, we're interested in the sign. Yes, sir.
So what's that first part, what you're doing there?
Uh-huh.
What is that called? Because you're just taking the derivative?
Right.
Solving for what?
So this was solving for the critical value,
Okay.
or critical point, yeah, the critical. Because I found where the first derivative is 0, and I know that's going to give me either a maximum or a minimum value. I took the second derivative test to figure out whether it's a maximum or a minimum.
So at that point you would solve for x.
Right. So I took its derivative and then I set the derivative equal to 0 and solve for x. Now, if it was a squared, there might be 2 places. If it's a cube, I could have 3 places where it's equal to 0. You know, so there could be multiple places, multiple critical values. It's nice when there's only one. Okay. So yeah, so I'm finding a critical point, took the first derivative, set it equal to 0. When I solve for x, that when x equals 1 tells me I've got a critical point, which means either minimum or maximum. I plug that into the second derivative to see if it's positive or negative. And in this case it was positive, so I know I have a minimum. And you could do the same thing if I had a negative in front of the x squared and you went through, your second derivative would have been negative 2. And you would see it's always going to be concave up, like concave down. So let's take g of x, right? So my first derivative is going to be negative 2x minus 2, and then my second derivative of g would simply be negative 2. So since the second derivative is always negative 2, it is concave down, so it would be a maximum. And that's what we've kind of, with x squared, if we see it's got a negative leading coefficient, it's always going to be concave down. All right? Oh. What does that mean when it won't go forward? It means that was the last slide. So, I wanted to, what time is it? Yeah, I've got a little bit of time. I just wanted to look at a couple of the homework together, see if there's any questions that come up. Basically, oh shoot, it did this to me last time, didn't it? Okay, maybe this will work. So 12.3, there's, I think, is it 12 or was it 15? I think there's 15, okay. So a few of the, I mean, they're going to give you a function and then they want the second derivative. You just have to remember you have to take the derivative twice. Take the derivative and then take the derivative of the derivative, put it in here, and you'll be fine. And again, you'll get slightly different numbers here. Again, what I would do here, rewrite this as x to the minus 2. So again, you're going to get more practice with taking derivatives again. And again, you'll see that all you're doing is you're taking a derivative of a derivative. So it's a 2 steps. You actually got 2 problems. These sometimes get confusing because remember, e to the x is its own derivative. So when you take the second derivative, it's still e to the x. But you'll see with this negative, that kind of pops on and off as you take a derivative because the negative comes down and then another negative and a negative of a negative is positive. But just kind of, that's all you're doing is going through. This one's actually fairly easy because it's always e to the x. But this little negative here will kind of oscillate on you, second derivative. This one, again, they give you a function. They just want it at, they first want you to get that second derivative. So again, you've got to take the derivative second time, and then plug in the value to that second derivative. So just some practice. Again, take the derivative, square root of t. We want to rewrite that as t to the 1/2. And again, you're going to have to take its derivative twice. And you'll see once you get to negative exponents, you take multiple exponents, that just becomes more and more negative, right? Because we keep subtracting 1. So by the second derivative, it's there. There is one where there's just kind of a picture, and you just kind of have to eyeball where you think the inflection point is, right? So, so it's just kind of, yeah, nothing we can do but sort of identify it. Another one where we can kind of try to guess where the inflection point might be. And again, that's where it goes from concave up to concave down or the other way. This one's a little more complicated, but I think you could see something there, some x values. And again, so graphical ways of looking for inflection points. Okay, remember that's just where it changes concavity. And then they're going to give you some functions. Again, finding the critical point. So that's the first derivative, where the first derivative equals 0. And you'll find that, but to figure out whether it's a maximum or minimum, that's what the second derivative could tell you. Or again, just graph it, right? You could do that. More of those, more practice, take the derivatives. Again, you're going to get 2 critical points. Again, I always like to graph it first and go through it, and then maybe try to do it again without graphing to see how it all connects. But, yeah, take the first derivative, second derivative. Few application problems. These get a little bit more funky. They give you a graph, matching up the graph. Where is it concave up? Where is it concave down? So that's a second derivative type thing. Does that seem all sort of doable? Okay, and we still got 15 minutes left after this, so if you've got any questions, you're welcome to hang out and get those. We will look at related rates on Thursday. We'll take a week off. Do take a break, but if you're a little bit behind, remember I've moved all the assignment deadlines, due dates to after spring break so that you can work on all the topics. And again, if you need something, let me know. We'll make it happen.